Good afternoon, I'm Jaehwi. I'm gonna be presenting our work entitled Jerk Minimized Autonomous Driving Strategy with Deep Reinforcement Learning. Here is a list of contents for today's presentation. I first introduce the motivation and background and delve into the proposed solution. Lastly, I will share the student's research and conclusion. Recent advances in autonomous driving technologies have allowed autonomous vehicles to navigate in real-world road environments. However, according to surveys, most people have reported the discomfort of riding in. Ride comfort is an important factor in the passenger's experience and should be considered in the context of the overall road environment, not just the specific road. So we use a reinforcement learning that enables instant decision-making based on surroundings. We aim to develop autonomous driving strategy for ensuring factors related to ride comfort. Reinforcement learning is a way for the agent to run a policy through interaction with the environment. First, the agent makes a decision in a certain state and receives reward from the environment, and it trains to polish and maximizes its cumulative reward. However, traditional reinforcement learning is difficult to apply in complex action spaces. To address this problem, we consider deep reinforcement learning, which uses a neural network as a function approximators. This makes it possible to handle problems with complex action spaces, for example, autonomous driving problem. Most reinforcement learning problems can be modeled as multiple decision process. MDPs assume that the agent has fully observable state information about its environment. However, in the real world, the agent cannot access complete state information, so we define the problem as a partially observable MDP, where the agent makes decisions based on partial observation. Next, jerk is a physical quantity that describes the rate of acceleration changes. In the graph on the left, you can see that the speed gradient changes, or rapid changes in acceleration increases the jerk. In other words, driving with rapid changes in acceleration leads to high jerk value, and many studies have confirmed that jerk causes discomfort at higher values. Our interest is to learn driving policies that minimize jerk across various scenarios. For this purpose, we consider 3 different scenarios: highway, cut-in, and on-level merging. In these scenarios, autonomous and non-autonomous vehicles coexist, and surroundings changes dynamically. So we aim to enable the agent to learn smooth driving based on deep reinforcement learning through our proposed MDP. The figure on the slide represents the visible area of the agent. Specifically, the agent can observe vehicles within H lanes and V stands front and rear. Vehicles that are not in this visible area are defined as unobservable. The observation OT consists of 5 different elements. Each element is described below. The observation performs to action, acceleration, and lane changing. In this case, the acceleration control has a continuous value within the range of minimum and maximum value. In addition, lane change has one of the following value: -1, 0, or 1. When -1, the agent changes to the right. When +1, it changes lanes to the left. And when value is 0, it stays in each lane. Next, the rear function consists of jerk, driving, and collision components. The first component is for minimizing jerk, which penalizes the agent for rapid changes in acceleration. In this situation, eta is a coefficient of this component. Through this component, the agent wants to drive smoothly and not generate high jerk. The second component is for successful driving in general situation. These components consist of 5 different reward terms in the below. Through these components, the agent runs each overall driving ability. The last collision component is designed to prevent accidents, and it penalizes the agent to causes an accident. We use flow traffic simulator to measure simulation results. We designed the traffic to be appropriate for each scenario. Let's take a look at the simulation results. We first compare the performance of the model that considers the jerk component and the model that does not consider it. In this figure, the x and y axis means the position of agent and jerk ratio. The jerk ratio represents the ratio of the actual measured value to the maximum possible value in the scenario. This result confirms that our proposed model that considering jerk component, the red, exhibits a significantly lower jerk value in all positions. Specifically, the performance gap is significant within 10 to 30 meters. This is because most range changing action happen in this range, causing rapid acceleration changes that result in high jerks. This table provides the numerical jerk ratio in all scenarios. This result shows that the model with the jerk component always measures the lower jerk ratio regardless of the driving scenarios. This means that considering jerk component is effective in learning driving policies that minimize jerk across various scenarios. Finally, to delve into how the jerk affects the driving, we check the change of speed as driving time. You can see the graph of the agent speed per time step in highway and cutting scenarios. This result confirms that the model without considering jerk component, the blue, has an unstable driving performance with high speed fluctuations, while the model with jerk component, the red, has a stable driving performance without a drastic speed change. Comprehensively, we find that jerk could result in unstable driving. In conclusion, we have an autonomous driving policy that minimizes jerk and provides stable driving in various scenarios using deep reinforcement running through our point P. We also confirm the effectiveness of the jerk component through an ability study. In future work, we will study multi-agent problems based on robust deep reinforcement learning. Thank you for listening.